Welcome back. Now we're going to wrap up our look at the theory behind homomorphic subgroups or subgroups of homomorphisms by looking at the commutator subgroup. And again, we're preparing the theory to dive into Rubik's Cube analysis. And so we've just covered conjugacy classes, and now we're going to look at the commutator. Those are the two main operations used. Okay, so first, we've seen a commutator a couple of times here and there, but I want to point out that there's two main ways to define a commutator. The main way we're going to use is A times B times A inverse times B inverse for the pairing AB. It is an operation of G cross G operating to G itself, but we want to think of it not necessarily as an operation this time. We saw that in the first exam. We want to think of it now as a group. What are the collection of elements we get out? Due to closure, we know that this output is in G. There's a similar version that we've seen before called the right action commutator, but we're going to focus on the left because basically they are identical in what they form and how they act. It's just, it gets a little confusing switching back and forth. So as long as you stick with one definition, all the properties hold as long as they're consistent. For the reason that we're going to use this form of it is that when you multiply the commutator on the left of the second element, you're able to cancel out the B inverse with B and reduce it down to AB A inverse. Now, why would you do that? Well, that's a conjugate of B. So the commutator times B is in the conjugacy class of B. Think about that for a second. So the product of a commutator, which has B as a second element, A as the first element, and with B, creates a conjugacy or a conjugate element. Now, because conjugacy classes are not groups, we can't say that, oh, that means the two elements are both conjugate to B. Unfortunately, not quite that much, but it does give us some properties that we can work with. Here's a little proposition we're going to work on as a class. Given a group G, the set of commutators, denoted by the commutator of G and big G and big G, is a set of all commutators of elements A and B that are in G. So if you collect together all the different results, what we call commutators, those are results of this operation, commutator operation on the two pieces, that set is a normal subgroup of G. And we call it the commutator subgroup or the derived group of G. It's a very special normal group, normal subgroup. And we've talked about this before. If G is abelian, then the operation is commutative. So the only output from commutators is the identity element, okay? The trivial group, if you think of it that way. So on the low end, we know that our commutator subgroup can be as low as the trivial group. Question is, how big can it be? And how does that bigness, size, relate to the matrix? Or sorry, not the matrix, relate to the group G. Well, let's just do an example here. Let G and H both be S3. We just talked about that, right? But now we're going to define a subgroup, G prime, which is the cyclic group formed from 1, 2, 3. And then we're going to define a homomorphism where theta of A is the commutator of A and 1, 2, 3, one of the elements in the group. Now, since G prime is cyclic, it is abelian by the corollary to theorem 14.2 on the fly. Look at that. So the subgroup of commutators of G prime is equal to 1 because it's abelian, right? We just said that. So what we can do is take this theta a theta homomorphism and restrict it to the subgroup G prime. Now this goes back to that first video on reviewing the basic homomorphism definitions and properties from section 23. So a restriction is simply just a restriction theta sub G prime is just a homomorphism whose domain has been restricted. Okay, so they're restricting the domain to G prime. So we're ignoring all elements A that come outside of this cyclic subgroup. And so this restriction theta sub G prime has the image of the identity permutation. So we know that it's a subset of the kernel of theta. Kind of cool, right? And so you should probably wonder, well, is it the kernel, or is it like, how big is the kernel of this transformation? Sorry, of this homomorphism defined by a commutator. My goodness, everything's just happening, isn't it? Well, if you think about it, 1, 2, 3 commutes with itself, its inverse, and the identity, right? So those three things are all in G prime. So it feels like there isn't anything else, but let's just see if we can prove that there's nothing else. So we're going to bring in the big guns. We're going to bring in Lagrange's theorem to show that the order of the kernel is first bounded between 3 and 6, between the subgroup that's contained inside of it and the group it's a subgroup of. But Lagrange's theorem that says that it can't be 4, can't be 5, because those don't divide 6. And so it must be either 3 or 6. And I worked through an example to show that one of the elements outside of G prime, the permutation 1, 2, gets mapped not to the identity permutation, but to, ironically, one of the elements in G prime. So it means that the kernel of theta cannot be 6 because we've taken one of the elements out. And so it must be 3. And that's the same as one of its subsets, which means the subset and the set are equal. Or I should say the subgroup and the group are equal in this case. So we found an example where we've restricted a homomorphism to only sending elements from its kernel. And thus, it is a homomorphism that takes everything to the identity element. And so we have a special name for this. Definition. A homomorphism, theta from G to H, is called a trivial homomorphism if the kernel of that homomorphism is the entire group G. Moreover, for any homomorphism, the restriction of theta subject to the kernel of theta, which basically takes just the kernel of theta to H, is always the trivial homomorphism. Put that in there, always. I think this is a term that we were trying to name last time. I think Caleb mentioned it. We should call it the kernel homomorphism. Well, actually, that has a name. So it's called the trivial homomorphism because it sends everything to the identity.